Dear learners, we are going to study the unit number 3, storage management today from the operating system. After going through this unit, you should be able to describe operating system services for memory management, understand how memory is allocated to the processes, understand many memory protection mechanisms, understand the concept of virtual memory and swapping, understand the advantages of paging and the segmentation, and to understand the concept of overlays and the page replacement policies. We are going to study the swapping, concept of swapping today. In the interactive system, because sometimes there is no enough memory available for the active processes, excess processes must be kept on the disk and brought in to runtime dynamically. Swapping is one of the memory management techniques in which each process is brought in its entirely and after running it for a while, putting it back on the disk to create the room for new incoming processes. The partitions can be variable, that means number, location and size of the partitions vary dynamically to improve the memory utilization. If you see the diagram A, there is operating system at the bottom and the process A is loaded in the memory. If you see the diagram B, operating system is there, process A is there, and B is loaded into the memory. In the diagram C, operating system A, B, and C is a new process loaded into the memory. In diagram D, operating system is there, process B is there, C is there, but process A terminated, and that memory is free for the new incoming process. If you see the diagram E, operating system is there, B is there, C is there, and process D is loaded into the memory at the place of the A. If you see the diagram F, process C is there, process D is there, again B is terminated, again process B is terminated to create the room for the new incoming process. And last diagram, if you see the G, process D is there, process C is there, operating system is there, and again process A is loaded into the memory, but at the other memory location. So it proves that every time the number of partitions in the memory are different, they are variable in size, and every time the process cannot be loaded at the same memory location, but they can change their location in the memory. So swapping may cause multiple holes in the memory, and these holes are not sufficient to load the new incoming processes. So we are combining that holes into the one big one by moving holes at the one side of the memory and the processes at the other side. That is known as a memory compaction. Swapping is slow. Also, it consumes many CPU cycles, but there is chance that data segment grow dynamically. So there should be a little extra memory whenever process is swapped. If there is no space in the memory when the process is going, they should be swapped out of the memory or killed. Issues with the variable partitions. How do we choose which hole to assign to the which process? That is allocation strategy. How do we manage memory to keep the track of holes? How do we avoid many small holes? One possible solution is compaction, but there are several variations of compaction. The question is which process should be moved. So we are going to study the memory management with bitmap. Here memory is divided into the allocation units as small as few words and as large as several kilobytes. Bitmap provides a simple way to keep the track of the memory words in a fixed amount of memory because size of the bitmap depends only on the size of the memory and size of the allocation unit. If the size of the allocation unit is large, the size of the bitmap is small, and if the size of the allocation units are small, the size of the bitmap will be large. The main problem is that when it has been decided to bring a K unit process into the memory management unit searches to find a run of a K 0 bits into map. This is a slow operation. Each allocation unit in the memory corresponds to the 1 bit in the bitmap. That is, if it is 0, the unit is free, and if it is 1, unit is occupied. The size of the allocation unit is important. The smaller allocation unit, the larger is bitmap. If the allocation unit is chosen large, the bitmap is smaller, but the process size is not an exact multiple of the allocation unit, the memory may be wasted. Keeping a track of memory to maintain a linked list is allocated and 3 memory segments where the segment is either process or boot. This is another technique that we are keeping the track of the memory by using the linked list. So we are keeping the linked list of a process and the whole. Each entry specifies a whole or a process, the address at which it starts, and the length and the pointer to the next entry. The list is sorted by the address because when the process is terminated or swapped out, updating the list is straightforward. This is a diagram. If you see, the memory is shown, and memory shows that at the beginning of the memory, there is process A, and process A occupies 5 allocation units. Then there is a free space, that is 3 allocation units are free. Then there is a process B into the memory. Then there is a process C. Then some memory is free. Then the process D is there. Then process E is there. And after that, some memory is free. So if you see the process, if you see the diagram B, here we'll find that bitmap is there, and bitmap contains either 0 or 1. If you see the for process A, there is 1, 1, 1, 1. 5 times 1 is there into the bitmap table, which indicates that the process is there and that allocation unit is occupied. After that, there are 3 allocation units are free. So if you see the bitmap, there are 3 zeros in the bitmap table. After that, process B is there and C is there. So we'll find that all ones are there into the bitmap. After that, 2 allocation units are free. So we'll find that 2 zeros are there. And after that, process D and E is there. So we'll find that 1 ones into the bitmap table. And after that, there are 3 allocation units which are free. So 3 zeros are there into the bitmap. So bitmap in the bitmap table, which shows either 1 or 0. 1 is there if allocation unit is occupied, and if 0 is there when the allocation unit is free. For example, suppose there is a request from the process which needs the 3 allocation units. Then, okay, memory management unit starts searching the bitmap from the beginning, and it will find that there will be 3 zeros. So immediately after the A process, he will find that 3 zeros are there, and that 3 allocation units will be occupied for the new incoming process. The same memory representation is shown in the diagram C with the help of a linked list. So P indicates the process, 0 indicates the starting, 5 indicates the total number of allocation units for the process, and next node is there that is pointing to the address to the next node. So if you see, next is a whole which is starting at 5, size of a 3, pointing to the next node. Then process B is there to P, starting at 8, size of a 6, pointing to the next node. Then again the process C is there to P, starting at 14, size of 4. Then next we have the 2 allocation units free. So it is H, that is whole, starting at 18, size of 2. Then we have the D process to P, starting at 20, size of a 6, pointing to the next node. Then again E is there to process P, that is 26, size of 3. And the last, that is EH is there, that whole is there, starting at 9, okay, size of 3, and we are not pointing into the next node, so cross is there. So how we are showing, the way we are showing the memory in the form of a linked list is shown in the diagram C. If you see, if the list is sorted by the addresses, the combination of the terminating the process X can be shown as follows. List update is different for each situation. Using double linked list is more convenient. So before X terminates and after X terminates, A, X, B, there are 3 nodes are there, And after X terminates, there are again the 3 nodes are there, but only X is going to be whole. In the diagram B, there are 3 nodes are there, A, X, and the third node is P, that is H is there. But when X terminates, this X and free memory is combined together, A will be there, so total number of nodes will be only 2. C diagram, free memory is there, X is there and B is there. So after termination of the X, again you'll find that X and the free memory combined together, and B is there, only 2 nodes will be there, means it is going to be shorter by 1 node. And if you see the diagram D, free memory is there, X process is there, and again the free memory is there. So when X terminates, there are 3 nodes will be converted to the single node. So size of the total number of nodes into the linked list, they are going to vary at the runtime, depending upon the runtime behavior of the processes. So this is a quiz time. Address generated by the CPU during the execution is known as. Swapping is the memory management technique in which processes are moved in and out of the dash to create a room for incoming processes. Processes of a moving process at one side and the whole at other side of the memory is known as dash. Memory is divided into dash are as small as few words and as large as several kilobytes. And dash is the best management technique as compared to the bitmap. Answers. Address generated by the CPU during the execution are referred as logical address or the virtual address. Swapping is a memory management technique in which processes are moved in and out of the memory to create the room for incoming processes. Process of a moving process at one side and whole at the other side of the memory is known as a compaction. Memory is divided into the allocation units as small as few words and as large as several kilobytes. And linked list is the best memory management technique as compared to the bitmap. We'll stop here today. Thank you very much.